I will record this and okay. We will done this and I will share this clip video to group number 1 also. Okay. For this, we subdivide the length. We subdivide the length. The length is the length of the beam is equal to 5 meters, right? We subdivide into small part of 1.25 meter, 1.25 meter. So what does it mean? It means that subdivide it into 4 parts, right? Okay, 1.25 is composed of 5 nodes. Composed of 5 nodes. This problem is the simple beam subject to distributed load. Simple beam subject to distributed load. Okay, and we can find the exact solution by direct integration. By direct integration, you use double integration, you obtain the solution over here. This is the solution. The solution is the 4th degree polynomial like this after second integration. Okay, you may derive this equation by yourself with the specified boundary condition over here. Okay, so we have a constant E, I, W, and L. Okay, from this, we may determine for, I should add the page. Okay, I already added. From the equation over here, from the equation, Golden equation of beam, how can we derive for the finite different equation? Okay, it has just only one differentiation term. So according to this, we have EI multiplied with yi plus 1 minus 2yi, okay, plus yi minus 1 divided by s squared, right, equal to WLX over 2 minus WX squared over 2, right? According to this equation, we can rearrange this equation to be yi plus 1 minus 2yi plus yi minus 1 equal to what? Equal to s squared over ei, right? Multiply with WLX over 2 minus WX squared over 2, right? This is the finite difference equation for each node. Okay, we may starting at node number 2. At node number 1, we know the value already at x equal to 0, y equal to 0, at x equal to L, y equal to 0, right? Okay, according to this equation, we have the finite difference equation over here, yi plus 1 minus 2yi plus yi minus 1, right, equal to s squared over ei. WLX over 2 minus WX squared over 2. Be careful for determine the constant for each value for the right hand side. The right hand side is composed of many constants that we can solve for a constant number. Okay, a constant number. So try to reduce the computation time, okay, by grouping some part of variable and determine it first, and after that you will not missing some term in calculation process. Okay, be careful on that. So for node number 2, we starting at node number 2. At node number 2, x is equal to what? X equal to 1. For this case, I use x equal to 125 centimeter. I use the unit of centimeter instead because I select the unit to be centimeter because it is easier than convert the unit to be meter. But for some students that would like to convert it to be meter, that is okay. That is okay. But I think because we have E elastic modulus in unit of KSC, that is kilogram per square centimeter. Okay, and I, that is moment of inertia in terms of centimeter powerful. Okay, so it may be easier to change just only the weight, the load. Form W is equal to 1000 kilogram per meter, right? So if we convert it to be kilogram per centimeter, we just divided by 100, so it's become 10 kilogram per centimeter, right? And length from 5 meter should be 500 centimeter. That is maybe easy for that. So for this case, I will note over here, H is become 125 centimeter. Length is become 500 centimeter. W, that is the weight, is 1000 kilogram per meter. That is become 10 kilogram per centimeter. E is 200,000 KSC, and I equal to 50,000 centimeter powerful. So we can conclude that EI is become 1 times 10 power 10 kilogram centimeter square. Okay, and finally we found that S square over EI, that is constant also, is equal to what? Over EI. It's become 1.5625 times 10 minus 6 per kilogram. Okay, we have all constant. Now we starting with node number 2. For node number 2, from this equation, what is it? From this equation, we obtain the equation of y3 rate minus 2y2 plus y1. Okay, but from the boundary condition, we know that y1 equal to 0. And it's become 1.5625. Okay, 10 minus 6. Okay, multiply with this value. You may recheck by yourself. Is equal to 234,375. Okay, you may check. Please help me. Someone help me, please. Check this term. Substitute W L X into this by using X equal to 125. Okay, after that, we got the equation y3 minus 2y2 equal to 0.5. This is equation 1, right? Do the same thing with node number 3. For node number 3, x is equal to what? X equal to 250 centimeter, right? So for node number 3, it's become y4 minus 2y3 plus y2 and equal to 0.48281. We check this value, okay? After that, finally, we have node 4. For node number 4, x equal to 375 centimeter, right? Then we have y5 minus 2y4 plus y3 equal to 0.366211. Okay, this term is become 0 because boundary condition. So finally, we have please check the constant that I have determined. Okay, then from these 3 equations, we can rewrite it into the metric form like this. You will see that the stiffness matrix over here is symmetry matrix. It is symmetric matrix. It's normally it should be symmetric. Then we solve for this equation. We obtain this is for numerical solution. We have to determine for the exact one. Exact solution is determined from what? It's determined from the formula that's given. That is y equal to WLX cubed over 12 EI minus WX4 over 24 EI minus WL cubed X over 24 EI. Okay, don't forget to substitute each value to this. Be careful in calculation. Okay, then we will obtain the exact solution for x equal to 125 centimeter. Substitute each value into this, you obtain y equal to minus 0.57. We check minus 0.577 834 centimeter. X equal to 250 centimeter. Okay, so then we can determine for the percent error in comparison with the numerical solution that we already obtained above. For the percent error for the case of Y2, okay, it's become actually the problem is symmetry, so you will see that the solution should be symmetry case. You see that according to the size of element that we subdivide, okay, equal to 125 centimeter, okay, we obtain the percent error approximately of 5%, okay, of 5%. The solution is not good enough. It should be subdivide the length, the size of the segment should be smaller than this, okay. But for the scope of the limit of time to solve the problem in 30 minutes, it should be just 4 elements. It should be enough for this, for the test. But actually, for the solution, for the better solution, we should subdivide the segment into the smaller segment, smaller part. Okay, do you understand? That's all for this problem.